Okay, good evening. So I thought we would spend a little time going through these homework problems from chapter 7. I'll briefly go through those, and if you guys have questions, you can email me or get in touch with me somehow. So I'm not going to read them like we typically do in class. Doesn't seem very appropriate for this format. So I'm hoping that you have them in front of you and you can take a look at them and go, follow along with me as we go through them. So number one is the Spider-Man problem. So Spider-Man is dangling from a rope and he starts the rope swinging and he gets himself going like you would on a swing by raising and lowering your legs, and he finally gets up enough energy to reach a certain height. And the key to this problem is, let's say that the rope is hanging, it's not very level. Let's say that the rope is hanging from here, okay? Here's a circular Spider-Man of mass M, and the rope has length L. And this is just like the pendulum problem that we've been talking about, where you have the difference in height for a simple pendulum. Okay, so you swing up to this point. This is still, and let's make the drawing a little bit better. Okay, that's pretty good. Better anyway. Okay, so you swing the mass up to this point. This is some angle theta, okay? And so this height, this difference between those two heights, call it y, all right? That difference will give you how much work is done by gravity, because you know the work done by gravity is equal to the change in potential energy, which in this case would be mgh. Okay. Is this going to be a positive amount of work done by gravity or a negative amount of work done by gravity? I think this is going to be a negative amount of work done by gravity. You're starting out here where the potential is equal to 0, or you can call this 0, and you're moving up to here to something above that. So the gravitational force was in this direction and the displacement was in this direction. That gives you a negative amount of work done by gravity. Okay. Nevertheless, let's look at what y is equal to, okay? This little bit of distance here is equal to, since this, when the object, Spider-Man, is at this angle or this distance, okay, then this bit of distance is L cosine theta, right? Because that would be the right triangle. This is the hypotenuse. This distance is L cosine theta. So y is just equal to L minus L cosine theta. Okay? And from that, you can determine the height of what the distance y is, that's a height, and you can determine the work done by gravity. Okay. Number 2. Number 2 is just a little exercise with taking dot products. So if you have two vectors in component, this is number 2. if you have two vectors in component form, A dot B, let's say they're three component vectors, you know that it's AX BX plus AY BY plus AZ BZ. Okay? Now, we also know that A dot B is equal to magnitude A, magnitude B, cosine theta. So these vectors are given to you in component form, A and B. Take the dot product in component form, that gives you some number. That number is equal to A, B, cosine theta. Okay? How do you figure out A? How do you figure out B? Well, how do you figure out the magnitude of a vector? Pretty simple. Okay. That's number 2. No big deal there. I think you can handle that. Number 3. This is the spring problem. All right. So the first thing you have to do is find K. I think they give you the displacement and they give you the force. So remember that S is equal to minus Kx. That's one dimension, right? That negative gives us the direction of the force. So the spring force is equal to minus Kx. You know the force, you know X, find K. Then they ask you, well, if you hang a different mass on there, how far will the spring stretch? From that, you figured out K, you now know the force, figure out X. I believe that's the way it goes. All right? And then you need to know the work done by some external agent in moving the spring. Remember, the work done by the spring is 1/2 Kx initial minus 1/2 Kx final. Okay? That's the work done by the spring. The work done on the spring is equal to the negative of that. External agent. Okay? So, once you calculate this, take the negative of it, and that's the work done by the external agent. Okay. Number 4. Number 4 is the rifle with the bullet, and I mean that one, it's just how much work is done, I think, on the bullet. Well, it's the integral of f dot dx, or yeah, make it a little vector, okay, from 0 up to x final. The angle between f and this little displacement vector is 0. Cosine 0 is 1, so this just is equal to the integral from 0 up to x final of f dx. And it's a force through a distance. The force is not constant, so you have to integrate it, and this force is of the form A plus bx plus c x squared. So when you do the problem, you have to integrate this. And then it's a definite integral. You're starting from 0 up to some x final. Calculate that definite integral, and that should do it. Okay? Number 5. Number 5 gives you some information about a particle moving between 2 points A and B. Okay? So the particle starts here and it moves to B. At A, you know the velocity. At B, you know the kinetic energy. All right? So for part A, nothing to do with this A, this is little a, part A. You know M, you know V, and you can calculate 1/2 mv squared. Because I think they asked for the kinetic energy at A. That's the way you calculate that. For part B, I believe they asked for the velocity at B. Simple. You know M, you know the kinetic energy, calculate V using this. Okay? Part C, how much work was done on the particle or the mass in moving from A to B? Work energy. Work is equal to the change in kinetic energy. That's going to be equal to the kinetic energy at B minus the kinetic energy at A. That's it. Some of these I know have tutorials, so it'll guide you, but maybe this will jumpstart you. Number 6. Number 6 is a little bit tricky. Do you know what a pile driver is? It's an old move in wrestling. Okay. When I was a kid. No, it's a big heavy weight. I'll call it Big M. And it falls down, and this is something in the ground, a pile, and they drop it and they drive this thing into the ground. Remember the demo I did with the nail and the heavy mass? And I said, well, if you had the mass and you were pounding the nail with the heavy mass, it would drive in much faster. That's the idea here. You have a heavy mass, you raise it, increase its potential energy, let it drop, bam. Okay? It hits the pile and drives it into the ground. Okay, so they're saying that you start out, I'm going to call this distance H. The heavy mass starts out at some distance H above the post or the pile that it's trying to drive into the ground. Then you let it drop. You let it drop, and as it drops, it contacts the post and it drives it a certain distance into the ground. I'm going to call that little distance Y. So here, let me see if I can squeeze this in here. This is not great, but okay. So the big mass comes down, it makes contact with the post and drives it a distance Y. There's a couple of ways that you could do this problem, I think. You have to think through it as far as what's happening. I want to look at it from the point of contact. Because from the point of contact, if I can figure out what that initial kinetic energy is, that initial potential energy is, and the final kinetic energy, the final potential energy, then that'll tell me how much work is done on Big M by this, okay? Let me look at it like, let's look at it like this. When it contacts the post, the work done by gravity plus the work done by the contact force is equal to the change in kinetic energy. And if we can figure out the work done by the contact force, then we can figure out the average force that was acting on the object through this distance. All right? So how much work is done by gravity? Well, that is mgy. It's falling. Gravity is doing a positive amount of work, okay, as after contact. I know it fell, I'm going to get to that, but after contact, gravity did a positive amount of work, okay, on big M. Oops, this should be big M. Okay, on big M. How much work was done by the contact force? Well, the contact force is what we're looking for, really, the average force. That did a negative amount of work, right? I didn't draw the free body diagram, but if I look at the force acting on big M from contact with the post, then that force was in that direction. The displacement was that way. So the work done by the contact force is F negative Fcy. Okay? So this is the work, and we need to look at the change in kinetic energy of big M. What's the initial kinetic energy for big M? Well, it fell from a height h before making contact with the post. Okay? Then the initial kinetic energy was equal to M, big M, not little m, mgh, right? Because it started out from a height h, that's all the energy it had before it made contact. So that initial kinetic energy, I'm talking about when it makes contact, is mgh. Go through the calculation if you want to. You started out here, you end here, that kinetic energy is going to be mgh, okay? Because that's the change in potential energy. The final kinetic energy is going to equal what? It comes to rest. 0. Now you can go back to this and figure out the contact force. You know M, that's the acceleration due to gravity. You know Y, you know H. The only unknown is the contact force. Don't forget that negative. Okay. Number 7. Number 7 is very straightforward. It's a stone falling into a well. I don't think you'll have any problems with number 7. If you do, let me know. I don't think you will. Number 8. Number 8, we really didn't talk about that much, but I went ahead and assigned it. If you have a potential function, u is some function of x, y, and z, okay? So that does not stand for force, that just stands for some function of x, y, and z. F based on this potential function is equal to minus du dx I hat plus minus du dy j hat plus negative du dz k hat. These are partials. If you've never seen partial derivatives before, that's fine. They're very simple as far as going through the motions of taking the partial. The partial says if you have a function, hold everything else constant except this variable x and differentiate with respect to x. Differentiate with respect to y only. Differentiate with respect to z only. You're looking at the rate of change of this function with respect to one of its variables. Example. Let's let f of x, y, z equal 3x cubed y squared z. If I want the partial of f with respect to x, I take the derivative with respect to x and hold everything else constant. That's going to be 9x squared y squared z. I just differentiated that and I tacked that back on. I held it constant. Partial of f with respect to y, that's equal to 6x cubed y z. Same thing. I held this constant, I held that constant, and I took the derivative with respect to y. It gave me a 6 out front, and that just became y. I'll squeeze in the partial of f with respect to z up here. Partial f with respect to z, 3x cubed y squared. And that's it. So that's all 8 problems. You can email me if you have troubles with these. I can go back over them. And I'll bid you adieu.